thing. See if the others cross notices. Do this. moving. But the room looks like it's freshly painted, so I guess worth it. Yeah. Took all the pencils out of the ceiling. All that. What's up? Oh yeah. Yeah. It's like over an hour. Probably like an hour and a half when we get there. It's past here for me. So I'd have to drive past here. Tough on the weekends with kid stuff too. Bless you. Two minutes. All right, it's 11. Let's get going. Looking pretty light today. I'm anticipating a lot of applause in a few minutes. So be ready. Not for me. You guys, come on, come on. Be serious. Let's be serious here for a moment. Okay. All right. Anyway, let's get started. Lord, thank you so much for just letting us get together today, and pray that you would help us to stay focused on the things that we need to do. Help us to remember that the best way to start any task that seems insurmountable is to do it one little piece at a time. In your name we pray. Amen. Right. Excellent. So what are we doing? We're going to do some statics today. We're going to recap. We're going to talk more about free body diagrams and equations of equilibrium as they apply specifically to rigid bodies as opposed to particles, right? Because we made it through particles fairly unscathed, right? And now we're in the realm of rigid bodies. We'll continue talking about 2 and 3 force members. Then we'll talk more about FBDs and equations of equilibrium again, and then hit constraints and statical determinacy. Determinacy. This might be a typo. We'll find out later. I think there's another N that's supposed to be in there. That's fine. All right. So moments. Moments seems to be the big ticket confusion here. I'm assuming since 3D is in there, it's 3D moments. But let's just talk about moments in general for the time being. Almost said for a moment. That would have been really confusing. Okay. So what is a moment? Some people call it a torque. If you're more comfortable thinking of it as a torque, that's fine. You can think of it as a torque. They're basically the same thing. It's a force applied at a distance, right? Whenever I apply a force at some distance away from the axis of rotation of a thing, I produce a moment, okay? And it is equivalent to a force times that distance that it is away in 2 dimensions, right? The perpendicular distance. So again, if I am to open the door, the further away I am, the further away I put the handle from the hinge, the easier of a time, presumably, I will have opening that door, unless you're at GCU and there's some strange HVAC issues that occur and it's impossible to open the doors because you're actually creating vacuum inside of the building. But that's a different story. I'm just talking about the door by itself, not the surrounding environment. Okay, so we physically and we intuitively understand that the further away I apply a force from something that's supposed to rotate, the less force I need to get the same amount of rotation, right? And that is the idea of a moment. Now, in statics, when we talk about this, we're talking about how do we physically oppose that rotation to create something that is stable, right? So we need to understand how applying forces to a thing creates all the different types of reactions that we would have, right? And one of those is a moment, right? So let's talk about fence post, right? If I have a fence post and I go to push on the top of the fence post, right? That's creating a moment around the base, but hopefully I have designed it such that I've designed it such that I have buried it deep enough that that moment gets counteracted by the ground, right? And if you were to push hard enough, it would eventually snap, right? But that's a material constraint. We're not really concerned about that. We just need to understand what is the driving mechanism that we're concerned about, right? And that is the moment. So in 3 dimensions, how does this play out? Well, it's not as intuitive in 3 dimensions, and we've seen that, right? And I would argue that the more of these that you do, you probably get a better sense of how rotations act in 3 dimensions, right? But at this point, we're new to the game, so our intuition for 3-dimensional moments isn't that good, and that's fine. But it's just doing a cross product, right? So if you book kept your vectors correctly, a moment is always r cross f, right? Where r is the distance vector between the point of we are interested in taking the moment about, so the hinge of the door, and the point where we are applying the force, which is the handle in that case, right? And so if you have multiple hinges on the door, you can find the moment to each of those hinges based on how much force, right? And they'll probably be each a little bit different, right? Because there's some angle associated with that vector, right? If you're hanging a sign on a signpost, right? There's things we don't often think about when we're doing that, right? Which is the wind. The wind blowing on the side of it causes another force, right? And that might be straight, it might not be straight at it, it might be at an angle, right? And now you've got a weird force vector, weird meaning that it is not perpendicular or normal to the plate that you are applying it to. And so now you've got these vectors that are at angles to each other, and how do we figure out how much rotation is happening in each of the axes? Trust your bookkeep. Remember, R always goes from where we are looking to any point on that force. Typically, we know the contact point where that force is being applied on anything that we are looking at, right? And so we can clearly make a vector there. And then, we have to be given, we're typically looking for a force, right, where we're given a moment, or you're told what the force is and you're trying to determine what the reaction has to be to counteract the application of that force, right? And we'll talk more about constraints and things later today in a minute. But in this case, right, remember, you can always, even if it's 2 dimensions, you can always use R cross F to find your moment, always. So I told you this on day 1, bookkeeping, right, making sure that we're accurately keeping track of our vectors, right, is really important. So as long as you're doing that, doing the cross product is not exceptionally difficult, right? Again, I'm not asking you to do triple integrals or solve differential equations, or I'm asking you to multiply and subtract and add. Okay? I feel like I feel that's fair. I'm going to be honest. I think that that's a fair expectation. Centroids. We didn't really go into centroids very much. A centroid, so this is where it's going to get, this is where it's weird, because we like to fundamentally say that I have to test every chair very carefully ever since last week. So we like to think that the center of gravity and the centroid align, right? That is in our brain. When I tell you the centroid, you're like, oh, that's the center of gravity of an object. Yes and no. It can be, it doesn't have to be. Okay? For the most part, if we have something that is made of uniform, a material of uniform density, then yes, they will align. But sometimes they don't, and we'll talk about that sort of stuff later, and we'll talk about how we define centroids. But for what we need to understand a centroid as being right now is it is the center of an area. Okay? So the 2 most commonly seen ones that we use are rectangles and triangles. We should all know how to find the area of a rectangle and a triangle. We went over it last time, right? Where is the centroid of a rectangle? It's dead center, right? Because the distribution of that area is uniform across the entire thing. So it's just right in the middle. When I say it's uniform across the entire thing, I mean if you go from left to right, it's very clear that the center of that rectangle would be the center of that rectangle, right, from on the x direction would be right in the middle, and vertically as well, right? As I move from top to bottom, the y direction center is in the middle. Both of those centers align at the centroid, right? Same deal with a triangle. If I were to find the center of the triangle from left to right, that's going to skew it towards, assuming that the fat end is towards the right, it's going to skew towards the fat end, right? Same deal as if I go from bottom to top. That starts to move it up. And so what we end up is we don't really typically care about the y direction of the centroid at this point, because we're applying it on the surface, right? We care where it falls on the surface. So that's 2/3 away from the skinny end or 1/3 away from the fat end. And that's because of how that area is distributed. You have more area towards the larger end of the triangle than towards the smaller, right? Okay. We use those so often that you will just end up remembering them. Like they are the two most common ones. We showed in class, well, what happens if I have a trapezoidal loading? Oh, that turns out to be two triangles and a rectangle. So we just break it into pieces, right? And you're like, well, it doesn't seem like it's very engineering of you. Well, it is. That's how when we get to the point where we're looking at actually finding centroids and you have to do the integral in the x in the y direction under the curve, turns out that we like to break things into shapes that we know as opposed to shapes that we don't know. So also turns out that a lot of these are tabulated for you, right? The centroids of areas are tabulated. And if you had a physical textbook, I would tell you to open up to the back cover and you would see them all right there. This is basically looks like that, right? That's handy. You guys have that in the digital form. You have to open up the actual digital textbook, which maybe you haven't, maybe you haven't. I would recommend at least, clicking on the PDF at some point, and then go all the way to the back cover, right? And you can get all that information too. Okay. Smooth. I try to be, but it doesn't really work out all the time. All right. Diagrams. Okay, rigid bodies. I'm not resonating with a bunch of this stuff. Is there anything that I missed on moments or anything else that's on here that really needs to be addressed absolutely right now before we move on? We will talk about, before we do this, we will talk about, what are we going to talk about? We're going to talk about your CLC project tomorrow. We're going to do a full rundown on the thing, okay? But if any of you saw the announcements, there's a couple announcements I posted yesterday. One of them is start thinking about your CLC team, maximum of 4 people per team, okay? Have one person, I'll remind you again tomorrow, but one person from each group respond to the DQ with who you want to be in there. Also, I know I said we weren't going to do any reviews, but plans change in your favor this time. And we will do a review tomorrow, like the last 45 minutes of class, okay? That's going to be driven by the questions you guys ask. And I posted a DQ in Halo about that as well. So any questions that you would like to be answered, I will try to answer as many of the ones that you guys post in Halo as I can by the end of class tomorrow, right? And if I can't by the end of class, if it's something that's super quick hitter, I might just respond in the DQ, right? But please feel free. I know some people have already posted some stuff. If it's about a specific problem, please include a picture of the problem too, just because it's going to be easier for me than trying to dig it up, right? If it's all in one spot. Okay, sound good? If you haven't started studying for the quiz, you should definitely do that now. But I would recommend. Before we get into that, let me hold on one sec here. Gotta see something. I didn't think I had that problem first, so you have to forgive me for a moment. I guess we are. We're doing that problem first. All right, cool. All right, well, let's do it then. As a form of review. Now, this doesn't really look like review to me. We're gonna come back to this because it's not review. Because it's asking for reaction forces. I don't think that we really talked about that yet. So we're gonna come back to that in a minute. Quiz on Thursday. If you were going to come to just one class this week, I would recommend that one, 100%. Okay, so definitely be here for that. Homework due on Sunday, then another homework due a couple weeks after, or is that a week after that? Yeah, on the 3rd. Those are both, I think that's a Sunday, the 25th, and the other one is Wednesday. Quiz 2 on the 5th, which is a Thursday. Quiz 2 will cover homeworks 3 and 4. Homework 5 on the 12th, and then there's your CLC stuff that's due on the 15th, and then we're gonna have a quiz the last day of class for fun times. We'll talk more about the CLC presentation and the design paper tomorrow. Okay. Okay. Here's my Dr. Deism for today. If you're not having fun, you're not doing it right, and that's just it's true. You should. All right. So my first semester teaching here, I would argue that I was more worried about making sure that everything was buttoned up than I was about actually making sure that people were learning. And for this particular job, if people aren't having, I have found that if people aren't engaged and having fun in some way, then they're typically shut down to learning. And so I would urge you that whatever you do when you get out of GCU, make sure that you are at least having fun in your own way, because there's nothing worse, and I've been there, than going to a job every day that you absolutely hate and asking yourself, why, God, did I do this to myself? Okay. So, a lot of people will say, find what you're passionate about, follow your dreams, all of that stuff. It all rolls into this. It's find something that you legitimately enjoy, even if it's the nerdiest thing in the world, then only you like it. It doesn't matter if everybody else likes your job. It matters if you like your job. Okay. Okay, great. Let's talk about free body diagrams. We already talked about free body diagrams. Guess what? Hasn't changed. It's the same as it always has been. There is a little bit of a difference here, though, right? We're going to go from I believe last time we talked about idealized models versus free body diagrams, right? An idealized model is basically the system picture that you get, right? The first picture that the textbook gives you. The free body diagram removes that thing from reality and then replaces things that we took out with forces, right? So again, this is our truck gate. I know we talked about that last time, and you'll see here at the end, instead of having our connection point, we've got our reaction forces. Okay. So what do we have to do? Well, we're going to draw our shape, right? We're going to imagine the body to be isolated or cut free from its constraints. And then we're going to show all the external forces in a couple moments, right? And so that's applied loads, support reactions, and the weight of the body. Last time we had just gotten to where we were going to start talking about reaction forces, I believe. So, all right, and then 3 is label your loads dimensions, right? So remember, we're dealing with vector quantities, so if you just draw them and you don't draw anything that gives you direction, like an angle or distance, you only have half the information that you need, right? So FBDs need to have dimensions on them. Okay. All right, let's talk about the different types of supports. This is a roller. It is called a roller because it looks like a roller. We can also think of this as a rocker. What is a roller designed to do? Well, something should roll on it, right? So think of it this way, right? We see that this reaction force here is completely vertical, right? Why? Because what is resisting our motion? Last time we said reactions was RPM, reactions prohibit motion, right? Something to that effect. I don't even remember what I put in there. Think about how this is allowed to move on a roller. It is allowed to move left and right? We are not resisting that motion. But we certainly do not want it lifting up off of the ground, right? And so the only reaction we have here is, in fact, from it sitting on the ground, okay? That normal force there. So a roller or a rocker will always have a single reaction force normal to the surface that we are touching. Okay? Always. Here's a pin support. Okay? Great. So what is a pin designed to do? Well, if I pin something, it's like this, right? Can this move left or right? Can it move left or right? No? I would hope not. Yeah, I mean, you would break it, right? Without breaking. So there should be a force resisting movement in the horizontal direction, right? What about up and down? Well, should stay fixed. The pin is there to keep this fixed in space. It is, however, allowed to rotate. So our reactions are a force in the x and a force in the y. Or you can draw it as a force with an angle, right? Because that's the same thing and we understand that. But there is no reaction moment, right? There is no reaction moment. Great, that's a pin. Those are probably the two most common types that you will see, right? But there are quite a few others, and we'll talk about those in a second. All right, more on FBDs. The first step, right, this is all the same. This is basically here to remind you that drawing a free body diagram is the same whether we do this for this crane or for a particle, right? It's all the same, except that in this case now, notice what we have. What kind of connection is this at A? It's a pin. What's this guy down at B? I can't really tell. This signifies a rocker, right? And you can see it's kind of rounded on the bottom. It looks like a triangle with a round bottom, right? Or like we took a piece of pie or whatever you want to think of it as. But it's allowed to rock on that, okay? So we could draw a free body diagram for this later, and we will. So the first step for static equilibrium analysis of a rigid body is cut it away from its supports and draw our, right? So we'll just do a quick example here, right? So here's point A, here's point B. Remember, we always want to have our coordinate axes nearby. Call this A and B. If we're going to draw this system, we'll do our best here. Go up to the pulley. There's a weight hanging from the pulley. Right, this kind of converges up there. Here's our center of gravity, point G, right? We got to draw our reactions. We said that we'll call this guy creatively Bx because it is the reaction of point B in the x direction. There is no By because rockers and rollers only have reactions in the normal direction to where we are making contact. Okay. This is a pin. We'll have AY and AX. That's an A, not a delta. Here's our weight. So I'm going to call that weight. And we have all of our distances, right? We can say we're missing one, right? There's probably the weight of the crane itself too. So I'll call this weight sub G. And we can say, well, I know this distance as 2 meters. This distance here, 4 meters. And this distance, which I've conveniently drawn my coordinate axes in, is 1.5 meters. And there's our free body diagram. It takes care of everything. I want you to notice one thing. Presumably, if we had this crane, we would know how much it weighs. We can figure out the weight of our Acme brand mast that is hanging there, okay? Because for some reason, we're at a construction site and we're trying to trap the Roadrunner, apparently, okay? How many unknowns do we have based off of these reactions? We have 3 reactions So we have three unknowns, okay? It is most likely in the real world that you would know how heavy the thing is that you're trying to pick up and how heavy the thing is that you have. There are cases in the textbook because of academic problems where they'll say, well, hey, you have this reaction force, determine what the heaviest load you can pick up is. That's not really how it works in the real world. Again, you need to know what those reactions are to make sure that you're not going over material limits, right? To make sure that you're actually going to be able to hold the thing up that you've picked up. But, anyway, three equations, three unknowns is pretty standard operating procedure. Oh, there it was. There's a better picture. And look, they even calculated the stuff. Apparently, this is 9.81 kilonewtons, even though I wasn't given any information about it. So wherever I got this from, cool. Yeah, I mean, you can, it's like kind of weigh it with your hand. Right? But look, everything's just the way that we drew, right? If you don't know, like with these reactions, I do not know if that is the actual way that they are pointing. I assume positive to start, right? Why? The general convention is to assume that if you don't know, you make it positive, because if it comes out negative, you know it flips the opposite direction, right? If I started negative and it came out negative, that means that it's actually positive. So remember that when you're doing this math, negative doesn't mean that, negative means that you guessed wrong in the direction that you drew it. So if you draw it negative and it comes out negative, double negative is a positive, which is sometimes more confusing, which is why I would always tell you just assume that it's positive and we'll move on, right? Because then negative means negative and you're good. You don't have to remember anything or figure out any other things. Okay. Okay, here is a table. You also have a table like this in your textbook, table 5.1 in chapter 5 of your textbook. Should be the first table in chapter 5, hence the point 1. So these are all the common different types of reactions that we would have. Notice rollers and rockers, this is kind of what they look like. Also frictionless surfaces. If you have a frictionless surface, you have a reaction still from your point of contact, normal to that surface, right? So the left-hand side would be the type of, oh my gosh, the type of connection that you have, and the right-hand side is what the reaction looks like. Then you've got short cables and short links. This really goes for long cables and long links as well. In this class, when you get to, if you're a mechanical engineer or biomedical engineer and you start getting into like biomechanics and solid mechanics, long links and long cables present other problems that you have to deal with, but they're not statics problems. But guess what? If you have another, this is all this is saying is if you have a rigid body attached to it, that force has to be along the direction of that rigid body, right? So we talked about this already. Forces go along cables, forces go across short links. If I have a collar on a frictionless rod or a frictionless pin in a slot, this is similar to having a roller, right? Because it's constrained to move in a specific direction. So we will always have force that is in contact. What is this force, right? This is the force between here and the slot, or the force between the bar and the collar, right? Okay, that's the normal force, the contact force between those two, but it is allowed to move, right, along that bar. All right, here's some more. Frictionless pin or hinge, right? We talked about pins or rough surface, right? If you had a rough surface, you might have some friction that is opposing your motion, and so you would have two reactions there, right? And then the final one here is the fixed support. This is our fence post, right? If I jam a fence post into the ground, right, or a footing for a building, something of that nature, I have three reactions here. I've got two forces and a moment, because this is going to help resist the rotations as well. Okay. Cool. Again, table 5.1 in your textbook has more than you really want of these. In practice, we are going to see a lot of rollers and a lot of pins in this class. So there you go. You'll see fixed supports too. Typically when we talk about beams, right, you'll see fixed supports. But those are the three most common. Do I expect you to remember all these? You're going to do so many that you probably just, I don't expect you guys to memorize anything. But I would hope that you understand what we're getting at here, right? And so if you don't want to memorize that, that's fine. I wouldn't tell you to. But remember what this is showing us. This is all about degrees of freedom or range of motion, right? So how do these connections allow for movement? If it lets you move in a specific direction, then you don't have a reaction. If you're opposing movement, then you have reaction, okay? So just think it through. All right, let's you know what, we're gonna go back. Let's just start here. It's fine. Maybe. Yeah, that's the one. Okay, that one, I think this one was this is a fun one. Here we go. All right, so the operator applies a vertical force to the pedal so that the spring is stretched 1.5 inches in, and the force in the short link at B is 20 pound to the right. Okay, so we're told how much force we have in the link B. We're told what the spring constant is and how much this has deflected, right? We want to draw a free body diagram for this foot pedal. That's what we're going to do. We're also going to solve for the forces because it's more fun. That's really it. All right. So first things first, let's draw a free body diagram. Here's our idealized model, right? That's great. Looking at this, what forces, where am I cutting it, right? That's a good question to ask. Well, we want to find the force in the spring and the reactions, right? So we're going to cut it like that. And we're going to remove that support. What kind of support is that at A? Yep, it's a pin. How can you tell that that's a pin? Because it looks like a pin. That's how you can tell. But in all seriousness, if you look at that, I think you can tell that you should be able to rotate there, and that specific support is there to make sure that we are only rotating and we're not moving in the horizontal or the vertical, right? Okay. Let's draw the FBD. This is there. Here's my force, F. We have to have our reactions. So at point A, I'm going to have AY and AX. We know that we have some spring force here. I'll call it very creatively F sub K. And then our last one at point B, we have FB. There's our free body diagram. Looking at this and based on the things that we were given. Looking at this and based on the things that we were given, how many unknowns do we see here? 3. We have F that we don't know, we have AX and AY. We know the other two, or we can find the other two. right? We were straight up told what FB is, and we can figure out FK from the information that we're given. So write down what we know. I'm going to get a new slide here, maybe. Okay. Ooh, fancy. I take my free body diagram, put it up there. I'm going to complete it because I haven't completed it yet. So I don't have a coordinate axis and I don't have my there's my coordinate axis, and from the point of application to A, we've got 5 inches. And then this is 1 inch between A and K. And this is 1.5 inches. What do we know? Well, first thing we know is that FB is equal to 20 pounds. We also know that FK should equal K. Well, we write it as KX, but really, in reality, it's K delta X, right? It's the change. For a spring, it's important to know what the change is from the free length, right? In this case, we were just told that it moves 1.5 inches. So we're going to assume that when it is not, that is the total change from the free length because it wasn't specified. There will be other problems where you'll be told, hey, check this out. The free length of this spring is 1 inch and it has moved to it is now in this position, and it'll show you, well, it's stretched to 1.5 inches. So your delta is 1/2 of an inch. Okay, but in this case, we know what it is. 20 pounds per inch times 1.5 inches gives me 30 pounds, right? Did I choose this in the correct direction? Well, we're gonna find out, right? But let's think about it for a second. If I have a force that is pushing down on the left-hand side, that should cause this whole thing to pull back to the left, right? Everybody see that? If I push here, it's kind of causing this thing to rotate that way. Yeah. If it rotates that way, I'm stretching the spring, right? I'm putting tension on the spring. That means the spring wants to fight back to restore it to its original position. So the force of the spring is actually pointing to the right. So yes, I chose it in the correct direction. FB, same deal, reaction, right? If we're extending this to the left, I'm putting it in tension, which means that it's fighting. It's fighting us to pull back the other way. Remember, these forces that we're drawing are all about how the system reacts, right? It's all about how the system is reacting. Okay, this one's pretty straightforward, right? So we want to find F, AX, AY. So how are we going to do that? We have 3 equations, 3 unknowns, right? Okay. So first thing first, let's sum the forces in the x direction so that equal to 0. We find out that AX plus FK plus FB is equal to 0. Okay, well, we know FK and FB, so we can solve for AX, right? AX is going to be negative FK minus FB, which is negative 20 minus 30. So AX needs to be pointing to the left. Physically, what does that mean for us? Physically, this means that the force of B pulling back and the force of the spring pulling back needs to be counteracted by that pin, right? So that it will stay statically in this position. Great. Next one, sum the forces in the y direction, set that equal to 0. You get AY minus equals 0. That's going to be a problem because I don't know either of those things, but I do know that that means that AY is equal to that force, so that's cool. We'll leave that for a second. Our third equation, we're going to sum the moment. Bless you. Where are we going to sum the moment about? Well, this one is kind of a problem for us, the way this problem is set up. Why? Is it? Is it a problem at all? Eh, I think we're doable here, right? But do we have everything we need to solve for a moment? Where would we take the moment? Where would you guys want to take the moment? At A? Why? Mhm. Sure. I would take it at A because it cancels the most amount of things, right? Most amount of things. So if we take the moment at A, I don't have to worry about anything that passes through A, right? What's the moment due to F? Force times 5 inches. Is that positive or negative? It's positive. What about Fk? Positive or negative? Hmm? What about Fb? Fb is also negative. That's going to be 2.5 inches. All right, so we've got everything we need and solve this out, right? So we can say that F is equal to Fk times 1, which if I do the quick math on that, would be 30 pound inches or inch pounds, however you want to define it. Plus FB times 1.5, which, hey, we did that. That's also 30, right? Divided by 5, not S, but 5. Try that one more time. There we go, by 5. 60 divided by 5, last time I checked was 12. It's 12 pounds. Guess what? We did it, guys. We did. We found both of them. Amazing. And we assumed that they were in the correct, well, we didn't assume that F was downward. We were told F was downward, but they both came out positive, which means that confirms the direction that we drew them in, right? So there we have it. We have everything we need. Finished. Questions about that? So remember, 2 dimensions, you have 3 equations, right? Use sum of forces or sum of moments. You can actually do this by summing the moment 3 times if you want to. I don't think that that's a great idea. It's overly complex for what you need to do. But there are some situations that we'll talk about when we get to trusses where that might make sense, where we can eliminate a lot of things and it allows us to solve for things directly. All right, and so. Mhm. So if, let's say this is the base part, right? If I push down here and this was allowed to spin around that pin, it would cause a counterclockwise rotation, right? Yes. So sometimes, again, sometimes if you look in the book and look at the example problems that they work out, sometimes you'll see them say, well, I'm going to sum the moment, and I don't like this, but they do it, so I will show you. I'm going to sum the moment at A, but I'm going to assume that that's positive. And then they write it that way. And I don't like that because it goes against the right-hand rule. and frankly, the very fiber of everything that I was taught for multiple years. And maybe that's just me, you know, maybe it's fine, right? But the big thing, if you're going to do that, that's fine, right? But you need to remember that that means that if this were to come out as, you flip all these signs, right? You flip all these signs, that's fine. It'll work out. But if you were looking for the moment and it came out positive, that now means that you have a clockwise rotation. So you need to keep track of that because it's important. All right? Sure. Which is also why you always see me just do this because I acknowledge that that is a preference and you can use whatever coordinate system you like and define positive and negative however you like, but make sure you're keeping track of what those things mean physically, right? Okay. Any other questions? Yeah, sure. Oh, yeah, sorry. That's a good catch. So that is not 30 anymore. That should be 50 now. Oh man, that's gonna mess up my math. That's 80 divided by 5. Jeez. Yeah. 16. I was shortchanging us. Apologize. Good catch. Thank you. Okay. Now we're supposed to do that other problem from the beginning. Let's see if it's still in here coming up. That should be fun. All right. Anything else? Well, I guess before I delete it. Anything else? No, we good? We good? Maybe. All right. All right. So get your whiteboards. If the direction of the force and couple moments are both reversed, what will happen to this beam? All right, so the couple moment here is the applied moment. That's what they're talking about, the blue moment. So if we reverse both the moment direction and the direction of the force, what happens? The beam will lift up from A, the beam will lift at B, the beam will be restrained, or the beam will break. What do you guys think? Ooh. Oh, yeah. Mhm. All right, we got a combination of A's and B's, it's looking like. Man. Well, we don't have enough information to know if the beam will break or not, because that's not the point of this class. Maybe, maybe not. We don't know. All right. C, the beam will be restrained. I mean, the answer is A. It'll lift from A. It can't lift from B, right? It can't. That's the whole point of the pin, is that it can't lift from point B without breaking. So I guess it can't. If A happens, then D also or sorry, if B happens, then D is also correct. Okay, it would have to be B and D. Okay, here's a question for you guys. What else prevents motion? Friction. Here's a follow-up question. Why am I not plummeting to the center of the earth right now? Yeah, the normal force. It's the same reason why when Spider-Man lands and he only uses one hand, the ground is fine and everything's cool. The ground, the table, right? So reactions there similar to rockers and rollers. right? If you have contact with something, there has to be a force as a reaction. So a normal force is a reaction, okay? So for part of your participation today, we're going to do this. I didn't bring any paper. You know what? Hang tight on this for a second. We'll bring this back up at the end of class where it makes sense to do it. All right, cool. Let's talk about equations of equilibrium. 2D conditions can be represented by three scalar equations. Remember, whenever we break down into components, we are talking about scalars. We've been doing this. Sum of forces X, sum of forces Y, sum of the moments about some arbitrary point O, right? Which is a horrible name because some people think that that means the origin, which it could be, but it's just any point. O, you can call it P, whatever you want. Okay, so if we have our potato here and we sum all of our forces X, Y, moments about any point that we're interested in, we can find the solution to the unknowns, right? This also constrains us to 2D problems to being able to have three equations with three unknowns, right? Because I can't ask you to, well, I could, but you wouldn't be able to do it, right? Unless we had a fourth equation for a fourth unknown. And there will be times when we will talk about that as well, but really, it's any of these equations that you can use. And like I've said before, right, if I took the moment about multiple places, I could do that 3 times and still fulfill the equations of equilibrium, okay? And sometimes that makes sense and sometimes it doesn't. Okay, 2 members and 3 force members. We're building toward trusses, right? So, okay. Some equilibrium problems can be simplified if we recognize that certain members that they are constructed of are subjected to force at only 2 points. Hence the very fancy and tricky name of the 2-force member. Subjected to force at only 2 points. What if I had a force here? Not a 2-force member. It's only 2 forces. You only get 2 forces on a 2-force member. All right, if we apply equations of equilibrium to such a member, we can quickly determine that the resultant forces at A and B must be equal in magnitude and act in the opposite directions. This is the idea, or along the line joining the points. So if you had a curved 2-force member as such, and you were to pull on the ends, the force along the line of action that connects both of those forces is equal and opposite, right? So that assumes that it is not breaking, right? If it's in static equilibrium and I pull on it, the force should be equal and opposite on both sides, right? This illustrates us putting something into tension because we are physically pulling the 2 sides apart from each other, right? Here's some examples of 2-force members in real life, IRL, if you will. In the cases above, members A, B can be considered as 2-force members provided that their weight is neglected. Is that okay to do? Yes. Why? Well, typically compared to the whole of the machine, the weight of that member is negligible. I don't know exactly what the rest of this looks like, but this looks like a digger, right? And so I would assume that the rest of the arm of that digger and the basket far outweighs this linkage from A to B, right? I would think that's a safe assumption there. But we want to know, in many cases, how is force transmitted through this, right? How much force is that carrying? Did we overload it? Is it going to bend? Is it going to break? And the process for doing that is doing a static equilibrium on it, right? So now that we know that's a 2-force member, and same deal here, we know that there's a force at A and a force at B, right? We're not worried about any of there's no other connection points. We can't transmit force through this in any other way, right? We have to apply a force at A and at B in order to do that. Okay. So if we want to solve these problems, what do we do? Right? If you don't know it, then set up an XY coordinate system. I would say, I mean, I pulled this from the textbook. I think that that's horrible advice. I think that you should always do this regardless of whether or not it's given to you. You should always write this down, right? Make sure even if it's given to you, you should make sure that you're cool with what's given to you, right? You guys are free thinking adults. I've told you, you can use whatever coordinate system you want. If one makes more sense to you than another, that's cool, right? But you got to draw it. Otherwise, I'm going to use the one that makes sense to me. Then we draw the free body diagram of the object that we have under analysis, and then we apply our three equations of equilibrium and solve for our unknowns. Okay. Pretty straightforward, and it's very rinse and repeat to everything that we've been doing up until this point, right? Draw the FBD with your coordinate system, write your sum of forces x, sum of forces y, sum of moments, solve your three equations, three unknowns. Sometimes they fall out really nicely, sometimes they don't, and sometimes we have to do some algebra, and that's that. We talked about this a lot. I say this like every time, right? But remember that when you use these equations, they are scalar equations, and so if it comes out negative, that is just telling you that you have to draw it in the other direction, right? So keep track of you will start seeing me write down this goes to the left, this goes to the right. Instead of me redrawing the whole free body diagram at the end, I just keep track of it with my answer. And that's fine. You can also redraw the free body diagram if you really want to. That's up to you, right? So again, the reason why I assume everything is positive, unless I am absolutely sure that it is not, right, is because if I get a negative, it's a simple matter of me understanding that I just chose wrong, as opposed to me choosing it negative and then it comes out negative and then I have to draw it positive, right? So it's a bookkeeping thing. I understand that you can draw it however you like, but you guys got to be responsible for tracking the correct sign of what we're talking about. Okay. So here's some real statics for you. All right, so what we got going on here? We were asked to find the support reactions at A and C. Now, before we get into this, if I asked you to find the support reactions at A and D, can you? How many unknowns do you have? It'd be 4. That seems like a problem. What about at C? Less of a problem. Why? What kind of reaction do we get from, what's the difference between point D and point C? They both look like pins, right? But what's the difference? There's a significant difference. The two-force thing. So CD is a short link, right? Meaning that we have one force that travels along the length of the link. Point D specifically is a pin. Pins have two reactions. So that's the main difference there, right? And so you can argue and say, well, Dr. D, I know what the angle would be there, so I could just write it as F from D to C. Could, right? It should be the same as F from C to D. But that's where the trick is here, is recognizing that you can write it as a single force as opposed to an X and a Y combination, okay? So that seems like a trick, kind of is. All right, so first things first, free body diagram. Let's punch that out. And I will go back to that other thing so you guys can draw that free body diagram later. So if I'm going to be really, if I'm going to draw a really slick three body diagram here, which, is very important. Here we go. There's my beam. And I've got some force over here pushing down on the end and that's 4 kilonewtons, and that's point B. And at point A, I will have AX and a y. And it's hard to tell, but point C is supposed to be in line with point A. It's hard to, you can kind of see it here. See, there's like a line. If I went back a slide, it'd be easy to see. See how there's this line here? So these are supposed to be in line with one another. So it's on the center of the beam. I know it looks a little weird because they have a cutout down here. And that's going to be pointed back towards D, and I will call this F from C to D. And I've assumed that that is in tension. How do I know that I've assumed that that's in tension? Because if this bar, if this beam, we're pulling on that bar, right? The reaction to that would be a force to restore it downward, right? So remember, it's not about, I know if you were to look at the bar itself, right, there would be an equal and opposite force going that way. But remember, it's not about the force that we're applying, it's about the reaction that we are maintaining, right? So if this is in tension, everything should be pulling it back to the wall. We also know some distances that we can write down. I will put point D down here just for completeness because I have a distance from point D to point A of 1.5 meters. From A to C, 1.5 meters. And there we go. 1.5 meters. Great. Things that we know. I have a force of 4 kilonewtons. And I've got some dimensions. Things that are unknown or that I've been asked to find, or the reactions at A and C, right? So AX, AY, FCD. Okay. I am going to consider this to be, well, I'm going to pause that for a moment. House, go out the door to the left. Okay, that was fun. So, okay, here's our free body diagram. We got three unknowns. We've got AX, AY, and FCD. We've got our dimensions. We've got everything we need. We need to find our three unknowns. So three equations, three unknowns. All right, so what do you guys want to do first? Sum forces X, Y, or take a moment? What do you want to do? X, all right. Well, first I gotta put the pen on first. That would help. So we sum the forces in the X direction. Set that equal to 0. That equals 0. We got AX minus FCD, the component in the X direction. What's the component of FCD in the X direction? Sure, FCD cosine of theta, right? Can we figure out what theta is? Mhm. Right. So you could say it's the cosine of theta, right? So cosine would be over hypotenuse. If both legs are 1.5, I would guess that the hypotenuse is 1.5 root 2, given it's a 45, 45, 90 triangle. That's 45 degrees. And we know that because both of the legs are the same, so they have to be 45 degrees. So cosine 45 degrees or 0.7071 and continue, right? There we go. We don't know either of those, so that's just going to be our equation 1. And we'll move on to some of the forces in the y direction. Very similarly, go. And then we have to take a moment. Where should we sum the moment? Where would you guys sum the moment if since you are going to? Well, just pull the audience. I use this specific point, but you can do it anywhere, right? So, oh, I forgot a force there. Yeah, erase it. Minus 4 kilonewtons. There you go. Okay. Where do you guys want to take the moment? Yeah. Yeah. You could do it at A, sure. I did it at C. Why would I do it at C instead of A? Well, AX passes through C, and I don't feel like dealing with cosine and sine components to figure out the moments, the Y component for FCD. So I just have to worry about AY if I use C. Does it matter? No. You eliminate the same number of components. It's 45-degree angle. You already know that it's FCD sine 45, right? Like it's not a big deal. Either you know enough both ways. But I chose C. If you use C, then the moment from AY. All right, so I'm at point C. I'm taking the moment. What's the moment produced by the force AY? What was that? Right. AY we have is 1.5. Is that positive or negative? It is negative. Remember, if I'm at point C and I push upward, that wants to force a clockwise rotation. Clockwise in the way that I have defined it is negative, so we would have a negative moment. Does everybody see how we got that moment? Does everybody understand how to determine that? Because it's the thing that's going to keep popping up, right? Then we have one more force that we have to worry about, which is the 4 kilonewton force, okay? what is the moment due to the 4 kilonewton force? How would I calculate it? Don't worry about positive or negative. Just how do I find it? How do I find a moment in general? Sure. And now now that we've figured that out, let's assign, remember, it's the force times the distance it is away perpendicularly from our point of interest, right? It's 1.5 meters. Is this a positive or a negative? It's negative. If I push down on the end with respect to point C, that would force a clockwise rotation. 3 equations, 3 unknowns. I'm going to solve equation 3 immediately. Yeah. Mhm. So why don't you consider AX? Because when you draw this, the original diagram indicated that A and C are in plane, right? So these 2 points pass through, like a line would pass through both of these points in the center, right? And so if I move, remember I can move a force vector anywhere along its line of action. So AX passes through point C, and so its perpendicular distance from point C is 0. All right. Good question. So we'll solve equation 3 because that lets me get AY right off the bat. Solving that says that AY is equal to 4 times 1.5 divided by 1.5. Those would cancel. That's 4 kilonewtons. That is very interesting. Should be negative. Should be negative. That's very interesting. That means I didn't draw it correctly, right? It needs to be pointing downward. We'll just make a note and move on. Great. Great and good. That's very interesting. Why is that very interesting? What does that indicate about the y component of CD? It has to be 0, right? Is that was weird? Is that true? Oh, we're gonna find out. All right, so we found that. So now what? Now we don't really have, I mean, now it's the next thing that we're gonna do, right, is we can solve equation 2, given all the information that we have, right? It's not, and it's not 0. They're both pointing down. So that means that FCD has to have 8 pointing up, right? It's not 0. 2 down, 1 up in the middle. Bounces. All right. So let's solve equation 2. Why did I go to equation 2? Because there's only one unknown. That's makes the most sense. You could solve equation 1 and then plug into equation 2, but we're not going to do that. We're going to solve equation 2 given the information that we have. Equation 2 tells me if I solve this for FCD, this is going to be equal to AY minus 4 divided by sine of 45 degrees, which is negative 4 minus 4 over the sine of 45 degrees, which allows us to see that FCD is negative 11.3 kilonewtons, and that is this way, or as I believe as Tyler had said just a moment ago, that it is actually in compression. It's not in tension. That's interesting. Why is that? It's not super important right now. It will be tomorrow, but it's not right now. When we start talking about trusses, it's going to be really important, whether we're in tension or compression. But for this in particular, right now, not. But it's interesting, right? Because we've got these forces pointing down, that means that in order to counterbalance my reaction and my applied force, this needs to react going this way, which means if you think about it, if I'm pushing down on these two things, right? I'm pushing down on the end, I should be compressing that, right? Doesn't that make sense? That this should be under compression and not in tension. If I was pulling up with 4 kilonewtons, yeah, I would expect that to be in tension. It's not right or wrong to assume either one, but now we can correct it and we move on, right? All right, and then the last one, we solve equation 1. And we find out that AX is equal to FCD times the cosine of 45 degrees. And so we plug in our things. Oh, no, incorrect. Okay, so in this case, because it is in compression, that means that our force flipped. And because our force flipped and is now going up and to the right, to counteract that in the x direction, it needs to be pushing back into the wall. We're getting this force that wants to push back out, so we have to pull back in. Okay. Notice that I plugged in the negative 11.3, not just 11.3. So keep the signs when you plug into your next equation. Don't just do the magnitude, right? Put the signs, well, technically it is the magnitude. Make sure you keep the signs as you have solved them when you plug back into other things. Because if you don't put negative, you're going to get positive, and it's going to tell you that that's pushing off the wall. But then if you did the sum of the forces, that wouldn't, it's not going to work for you. Right? So, okie dokie. Okie dokie. Very good. Questions, comments, concerns? No. Pretty straightforward, right? Hopefully. And a lot of this is going to be rinse and repeat, right? Draw a free body diagram for the whole system. Put in the reaction forces, put in all of your applied forces, put in your distances, set up your coordinate axis. Once you have the free body diagram, writing sum of forces and sum of moments is really easy, right? Which is why I'm trying to tell you guys that the free body diagram is so important. Because I have this, right? Because I have this, it's very simple for me to write out these equations, right? It has all of the information that I need to write it out. And so always have a free body diagram, always. All right, any questions on this right now? 'Cause I got another fun, like super fun one now. You guys are like, oh boy. Okay, now check this one out. Check out this beam. It's a pretty sweet beam. Can you still call that a beam? Yes, I can. I sure can. I just did. I did it. All right. So what do we got going on here, right? You look at this beam, and we want to find the reactions at A and B. Okay. First thing, what kind of connection do we have at point A? Roller. Excellent. What do we have at point B? Pin. Okay. And notice we have that beautiful distributed loading on the right half of our beam. It's so great. People love distributed loads. They're the best, right? All right, so let's start with our free body diagram of the entire system. Here's that's would be point A. And there's point B. This is not drawn to scale at all. I'll make my customary not drawn to scale comment. Great. We know angles. I'm going to put in my angles first. I know some distances from here to here. 3 meters. From here to here. 3 meters. Sorry, 4 meters. Geez. Maybe it is drawn to scale. No, it's not. Definitely not. All right, I didn't put the force in yet. What's the best way for me to represent this force? As a rectangle? As a single point? All right, show of hands. Who thinks leaving it as a rectangle is the way to go here? Not even David, who introduced the idea. Okay, who thinks that creating a single point load from this force is the way to go? Good choice. My biggest advice on any quiz or test or anything that you ever do is if you don't know what to do, do something. Okay. Just start doing something, which is why I tell you guys, draw your diagrams. Like I set it up. The reason I like to have an algorithm for how I approach problem solving is because in high stress situations, you stop thinking about how to do it and you just start doing, right? Have you guys ever seen the movie Semi-Pro with Will Ferrell? Okay. The reason you run the puke is to create muscle memory. Because when you're tired and you're stressed and you don't know what you're doing, you have something that your body will just automatically do. The reason that we approach, you don't have to use my version of solving a problem, that's fine. But I would highly encourage you to have a systematic approach to solving these problems so that if you get flustered, you just know I start with this and then you ease into it however you do it, okay? That being said, we have to set up a coordinate system here, but first let's create our point load. How much point load do I have? 12 kilonewtons. How do I know that? Well, it's the area under the curve, right? And the area under that curve is 3 kilonewtons per meter over 4 meters, which is 3 times 4. Cancel the meters. I'm left with 12 kilonewtons. Where does that apply? 2 meters from where? Well, the left is over here. Two meters from there. Okay, so now we have everything that we need except for a coordinate system. There's two possible choices. Well, there's an infinite number of choices that you can choose for your coordinate axes. I think that there are two that make the most sense here. You can either angle it at 30 degrees to be along A, from A to the corner, or you can leave it in a normal Cartesian coordinate system. And either way, you're going to have to deal with that 30 degrees at some point, right? So you can choose whatever you want, right? You can draw it however you like. I am going to just use our standard plain 90-degree angle X and Y, okay? Y is, again, doesn't really matter. We didn't put our reaction forces on here, right? AY, BY, and BX. There. There we have it. A complete free body diagram. Look, 3 unknowns. It's crazy. It's crazy. It's almost like these problems are designed so that we have to use 3 equations to do them. Amazing. All right. What do we know? Distributed load and dimensions. We want to find AY, BX, BY. All right, I'm going to give you guys 15 minutes to 1 o'clock. Work on it. I'll walk around. You guys doing okay? Any questions? All right. Sneak behind you. Yeah, it's okay.
It's gonna be X, right? And then do X equals.
So what direction is that force at AY pointing in? What's F then? What's F? But is there another force? So remember, you got to break everything into components of this coordinate system. That's good. That's all right. What's up? Hmm. You are. So, so remember, you have to have everything in the same coordinate system, right? So is the X direction 0?
Yeah.
But are all of your forces broken down into XY coordinates? So we're not calling it AX. I just called that AY, but you can call it whatever you like. But that component, that force at A, there's an X component and a Y component, right? So you have to figure out how much goes horizontal because it's at an angle, right? That gets you a distance, but that's not getting you the angle, right? You guys good?
I think so. It's more like sign issues that I'm dealing with.
Okay.
But I think
Like sign the function or negative?
like two times I'm picking the moment at B because it's from.
So think about the sense of the moment then completely. So you only put the negative on for the total, like, so if you're at B and you're pushing down, right? Yeah. Yep. Questions?
That.
I don't know. See, missing something in the X direction, but you accounted for it in the Y direction. You guys good? It's so convincing. You should have. Everything, if you're going to talk about the some of the forces in the X direction and you set up the X direction to be horizontal, then you need to have all of your forces in that coordinate system. If you need the perpendicular distance, then you need to have the cosine and sine. No. All right. Fantastic. Yes. Wait. Okay. We're good. Okay. Mm-hmm. Yeah. Okay. All right. Couple more minutes. All right. Everybody good? Everybody got something? Yeah. Yes. Everybody good? Good, good. Yes, no. You can say no if you're not good. It's fine. You need more time? You need a couple minutes? All right. Since I'm not hearing anything, we're going to keep going. Move with it. All right. So what's the deal here, right? Some are forces in the X and the Y, and we're going to take a moment, right? Notice I conveniently changed AY, and I changed the name of it to FA. Why? AY, it's not really in the Y direction. It's angled. What's that angled by? 30 degrees. And when you set a coordinate system, and this is an important thing, right, to remember, when we set our coordinate axis, we need to report everything in terms of that coordinate system, right? So everything needs to be reported in terms of x, y, where x is horizontal and y is vertical, not angled. Had we angled it at 30 degrees, and the reason why I didn't is because then there are 3 other forces that I need to do trig on instead of essentially one force that needs to be given the trig treatment, right? So now what? Of course, that's not going to work for me, right? So let's see if this works. There we go. First thing I'm going to do is I'm going to solve equation 3, which is my moment equation. I want you to notice the moment equation is pretty weird, right? So what we have going on? We got 12 times 2, right? That's our 12 kilonewtons. Well, let's do this. My 12 kilonewtons at 2 meters away from B. If I push down, that should give me a positive sense moment. So that's the 12 times 2. The other force that we have is FA or AY, right? I need to first break that down into the component of the force. So in the x direction, right, I have a force FA times sine of 30. Why is it the sine of 30? Well, let me draw something really quick. Because this is the angle we're talking about in here, and that's 30 degrees. Okay. But we have a double trig because we need the perpendicular distance, and we were given the 3 meters that's on an angle of 30 degrees. So we have to break that down into its x component, which is the 3 cosine 30. So we have 2. So if I'm going from B, I've got to go 2 plus 2 to get my 4 to get to the corner. And then from the corner, I need to go 3 cosine 30 to get my perpendicular distance for my y moment. Okay. Same thing in the other one. If I'm pushing up and to the left or up and to the right, that's going to cause a clockwise rotation, right? So both of those moments are going to be sensed in the negative direction. So equation 3, we move some things around. FA cosine 30 is the y component times the 6.6 meters away from B, right? FA sine of 30 is the x component, and it's 1.5 meters away from B. And you put all that together, you find that FA is 3.7 kilonewtons up and to the right. We knew that was going to be correct pretty much off the bat. Be very strange if by loading that at close to point B, you would get some force not balancing the positive, the y direction, all right? There we go. Yeah. Mm-hmm. So, all right, let me do it this way. So this force here, right? You can break this down into x and y components, right? So I've got some component that goes this way and some component that goes that way, right? At point A. The angle between the vertical, or let's draw it over here. This angle is 30 degrees. I know that that's 30 degrees because the x-axis is off by 30 degrees. I'm going to make this less cluttered. All right. Well, let's do that. Try that one more time. Sure. Sure thing. So here's point A. Okay. And B is over here. If I'm just worried about the moment due to A, I've got some force here and some force here, right? The perpendicular distance for each of these would be what? From point B, because that's where I'm taking the moment. Try that again. Well, I know that this much to here is 4 meters. And I have this 30 degrees, right? And I know that this length from here to here is 3 meters. But I need the x component. I need the rest of this. What's that? 3 times cosine of 30. Same distance, same deal here, right? From point B to this force is 3 times the sine of 30 degrees, right? Cool. Okay. So we can solve that out We just got to keep track of our distances, right? Then we have basically everything we need to go back through the other two equations and solve directly for the B force, right? And so we plug in here, get this, Bx is negative 1.86. So it's actually going to be pointed to the left. Why? Because this thing's allowed to roll a little bit in either direction. And so by pushing down on one side, if you think about what's going to happen, right? If I push down on the lower half, that's probably going to pull A towards us, right? And so B has to counteract that, okay? In the Y direction, we'll do that next. Solve equation 2. And we find out that B is going to be pointing up at 8. It says newtons. That should be kilonewtons because this whole problem's in kilonewtons. Notice I put my direction next to my force reporting, right? Over here. That is for me to understand the direction in which these forces actually go, because in practice, you need to know that, right? You could redraw a free body diagram with the correct sense of your forces if you wanted to. Okay. This one's a little bit more complicated for a couple reasons, right? One, you've got to track you've got a weird geometry. It's not impossible, just have to think of it a little bit, right? Figure out what you need to know. Again, that's where pictures help, right? You have a distributed load, which easy for us to figure out, right? And then we just have to make sure that we're following our trig, right? Break your things down. The big thing here is making sure that if we set a coordinate axis, if we say sum the forces in the x, that means in this direction, right? If I had angled this along A, then I would have had to you would have had to give me components of 12 kilonewtons in the x direction, right? And bx and by, same deal. You would have to angle that whole thing by 30. You can do it that way. It's fine. Just it's more trig that you have to kind of worry about. More things, more moving pieces typically means there are more opportunities for us to write something down that is incorrect, right? So try to keep it simple. All right. Questions on this? What if the distributed load had been along the entire thing? Oh boy, that's fun. You split the distributed load into two rectangles and you go from there. Okay. All right. Which equation of equilibrium allows you to determine FB right away? Some of the forces X, some of the forces Y, some of the moments at A, or any one of the above. What allows you to get FB immediately? We think A, B, C, D. Throw them up. Looks like we got mostly C's, some D's. All right. Answer is actually it's E. It's none of them because there's no distances on here, so you can't possibly calculate anything. No, it would be C, right? Why? Why is it C? If I had distances on here, it would be C. Why? Because that eliminates AX and AY. It leaves you only with FB, right? Only with FB. And we can just solve that immediately, right? So remember, always read what the question is asking you. If a question asks you specifically, hey, what in this sense, hey, what is the force at B? And it doesn't ask you for the reactions, You really don't even need to calculate them if you just use some of the moments at A. Right? But why? Okay, this is different now. Why is it different? Because we're going to talk about three-dimensional free body diagrams and three-dimensional connections. And that's sometimes super fun. So we've got ball and socket joints and journal bearings that are often used in mechanical systems. Ball and socket joints used in the human body quite a bit for your hip and your shoulder. Those are fun, super fun. Yeah, so there. So if you're given a three-dimensional problem, we need to understand how do these types of connections allow motion, right? That's the whole idea. In this case, right, if I have a tie rod, right, that's hanging from point A, and we use that to support the overhang of an entrance, right? We don't want that to fall, so we're going to need to figure out how much force can be taken up here and what our reaction looks like up at that point, right? Right. Then obviously, you have this floor crane that's used for lifting oil drums. You know what's a really important thing too is making sure maybe that you like don't puncture water lines. But anyway, how do you determine how much you can hoist, right? Like, so if you're part of GCU Motorsports, right, and you want to put your engine in your car, right? You need to make sure that you have a big enough hoist that allows you to actually hold the engine up and not tip over because you have too much moment and the wheels now. Right? As I understand it, those engines are expensive, from what I understand. No, not that bad. No, that's cool. No. No. Yeah. Okay. Well, anyway, what does reactions look like in 3D? Guess what? There's a table for this in your book also, which you can use. It's table 5.2. It's after table 5.1. I once had, so an aside, I once had a student ask me, I can't find figure 2.11 in the textbook. And they were looking in chapter 3. The first number tells you the chapter in the book that the figure or table comes from. And the second number tells you the order in which that appears. All right, so you are aware. So here's a few examples, right? We've got a smooth surface support. Guess what? A smooth surface support, it will shift anywhere. It will move however you want it to, right? It's on a smooth surface. Think about how things move on ice, right? They slide in every direction. They're also allowed to rotate. So the only constraint that we have is that we need to maintain normal force with the ground, because if we're not touching anything, there's no reaction, right? There's no reaction. Okay, ball and socket. Ball and socket's allowed to rotate around any axis, right? But if my shoulder got separated from my arm and the ball popped out of the socket, that would not only be very painful, but also is not how it's designed to move. You can't really move your arm if this is separated from your shoulder, right? So this has reactions of forces in the cardinal directions, but is allowed to rotate in multiple directions unless you have some other stuff constraining it, which your arm does. Single journal bearing. Bearings are where it gets a little bit weird, right? Because some bearings allow for rotation in one axis, but not the other two, and that's pretty standard, right? You can see, you would understand that, if this was the axle of your car and you want it to spin in one direction, you don't want it to spin in the other directions. That's pretty bad, right? But you also don't want it to move horizontally or vertically. Sometimes, as in the case of this bearing, this is allowed to slide in the Y direction here, right? But not up or back. And that happens in some cases. In your car axle, those bearings should not allow your axle to slide in that direction. That's not good, right? Hinge, right? If you have a single hinge, this isn't going to rotate in the X or the Z, right? It's allowed to rotate in one direction, but it shouldn't move in any of the other directions either, right? It should stay put, okay? Again, it's all about what supports allow for move. What are you allowed? How are you allowed to move, right? How are you allowed to move? A single bearing or hinge can prevent rotation by providing a resistive couple moment, right? We kind of talked about that here with the hinge and the bearing, right? This provides a resistant moment, right? That we'll have to figure out what that looks like. Two or more properly aligned bearings or hinges is the preferred way to do it. And there's a reason for that we'll talk about in a second. So how does this affect our equations of equilibrium? Well, now that we're in 3-dimension, we have 6 equations. Because we have some of the forces x, y, z, and some of the moments x, y, z. And that seems unfair because we only added 1 dimension, but 3 more equations. As a wise man once said, it is what it is. Okay. So now we have 6 scalar equations that we would take into account for doing our equilibrium analysis, right? And we have to balance everything, not just the forces x, y, z, but also the moments about the x, y, and z axes as well, okay? How do we set up these equations? The same way that we always set up these equations, right? You draw your free body diagram, right? Then you figure out what your knowns are, what are your unknowns, right? Maybe you draw a free body diagram for multiple axes, right? Draw an XY plane, a YZ plane, an XZ plane, right? All those things. But that's what we got to do, right? So I'm going to talk to you about constraints and statical determinacy. Right? Why? What does this even mean? When you do something in SolidWorks, okay? When you do something in SolidWorks, what happens if you over constrain it? It turns red, which means it's mad at you, right? Because SolidWorks has sentience, okay? Yeah, and it always wants more of your RAM, no matter how much you have. You could have infinite RAM, and it is the Galactus of programs. It is the world eater. Okay. Uh, anyway, so if you over constrain something, what happens? What happens if you have a redundant constraint, right? Because it tells you in SolidWorks, you have too many constraints. These 2 are redundant, right? You don't need to define all of these constraints, okay? Redundant constraints is when we have more supports than necessary to hold it in equilibrium. So you have extra things in there. And that's not necessarily bad, right? Because maybe you're anticipating multiple types of loading. So in a certain condition, something doesn't come into play. But if I were to flip how I put force on it, maybe then it comes into play, right? So redundant constraints are typically seen as really good, right? Well, not really good. They're seen as good because they allow us to have redundancy in our system, and it's typically a safety factor, right? The problem with them is that it becomes statically indeterminate. Now, that's a problem because that means you have more unknowns than you have equations, which means that you cannot solve it. Okay? Okay, more unknowns than equations is very bad. It's not very bad, it's just bad. You would say, oh, statically indeterminate, can't do this, right? Or do we use these in practice? Yes. Yes, we do. Why? Because we make certain assumptions in different orientations, right? Like I just said, there are certain cases, and we'll talk about this next class when we talk about trusses. There are certain times when, depending on the loading of something, you can make a case for why you know the force in specific members just by looking, by inspection. Improper constraints. This time we have 6 unknowns, and there's nothing restricting our rotation about the AB axis. Okay, so this is improper because it's just gonna rotate. You can't keep it statically constrained, right? As it shows here, it's an improper static constraint because the sum of our moments about this axis is non-zero, which makes it a dynamics problem. It doesn't make it a statics problem. So it's not that you can't solve it, it's just that you can't solve it in static equilibrium. Okay. In some cases, there may be as many unknown reactions as there are equilibrium equations. If the supports are not properly constrained, the body may become unstable. So it's a stability issue. And the bottom one here, again, it typically revolves around moments that are non-constrained, right? So if you were to look at this, your sum of your moments here would be a non-zero if you were doing it at A, right? Because now you've got just the P, right? All these other ones cancel out at A, but P is still going to have a moment. So it can't possibly be zero because it is not balancing with anything. What would this tell us? This would tell us that this constraint is not the right constraint to use, right? We would want to use a fixed point here, not a pin, right? Because the fixed point produces a counter moment that allows us to keep it stable, okay? Again, number of unknowns is equal to the number of equations here, right? But we can't really do anything about it because the constraint's improper. Yeah, no, we don't have time for that one. We'll do that next class. It's fine. This is, yeah, we'll do this next class. Start that there. That one too. It's fine. Okay. We'll do the whiteboard question though and see. Just see how everybody's doing. Rod AB is supported using two cables at B and a ball and socket joint at A. Okay, so it's two cables at B and a ball and socket joint. How many unknown support reactions exist in this problem? Okay. So, I mean, you have a few choices here, right? How many unknown support reactions exist? So remember, think about how this is allowed to move, right? Think about what directions are constrained. What reactions are we looking for? What's a ball and socket joint allow you to do? How does force transmit along cables? Got some A's, some C's, some D's, a B. Okay, pretty much running the game and throw them up. Whatever you got. Yep, it says dad over there. Nice. Okay. So mostly A's and D's. I got a B and a C. The answer is B. It's B. Why is it B? Yeah. Yeah, it's not Jeopardy where the bottom half is your wager. Okay. Why is it B? Why is it 5? Why is it 5? What does a ball and socket joint allow us to do? Does it allow for rotations in all? Yeah, so there's no moments that are reacting there, but it stop X, Y, and Z motion, right? So there's three forces right there. Cables. We don't really talk about moments on cables, right? Because if I start to bend a cable, bad things happen. It's not designed to work in, they're designed to work in tension only. And so there have to be forces that come off of those and no moments, 2 more. So it's 5. Okay, 5 reactions. All of them forces. Yeah. Yes. But they're all forces. There's no moments. Because it's allowed, if the cables weren't there, right, you could rotate that in around any of the axes that you wanted because of the nature of a ball and socket joint. Okay. Yep. Oh, sorry. There was another one. Yeah, it's D. In addition to a couple moment in the vertical direction, in addition, if an additional couple moment in the vertical direction is applied to rod AB at point C, then what will happen to the rod? So if we put at point C, we put a moment on here, right? Then I'll show you guys. The rod becomes unstable since the moment about AB cannot be restricted, right? If we put a moment on here, right? If we have a couple moment, right? So if you do that with a force at a known distance, or just say I'm going to twist it, right? It becomes unstable. Why? Because there is no reaction here that can handle a moment in any direction. So we would need to change the system at the ball and socket or one of the cables out for something that can create a moment reaction. Okay? So if you start doing these problems and you see, hey, I can't, I'm getting non-zero for the sum of my moments, check to see if you're statically determinate. Most of the time, the problems are not. I think it's an interesting case to look at, and it's important for you guys to be able to pick out when something is not working and the reason why, right? And it's an actual application, right? If you were going to design this in the real world, you're expecting some sort of moment on here, you need to understand that the type of connection point that you use matters for being able to actually handle that, right? Because no matter the direction, right? Let's say I put a moment on here. Let's say I start spinning this thing about this axis, right? So I'm just twisting it in there. There's nothing to stop it. And what's going to happen? You're going to wrap up those cables and the whole thing's going to break, right? Same deal is if I started rotating it upward. If I start moving it up like that, what's going to happen? Those cables are eventually going to break because there's no way to counteract any of those moments with this. Okay. All right. Good talk. Oh, there you go. There we go. That's gonna be it for today. Next class, we will pick up from here. We will start talking about trusses. Okay, we're actually going to start talking about structural analysis next class. Okay. Last 45 minutes of next class, you will get to ask questions for relating to the quiz. Please come prepared because it is driven by you guys, not by me. I don't know what's giving you problems. You know what's giving you problems. Okay. Use the discussion question to post any questions that you have or that you want to be answered either as part of the review or in general. Quiz is on Thursday. Definitely come to that class. Would recommend 10 out of 10. I hope there's no more fire alarms. If there is, we'll figure it out. Next class at the beginning, I will go over the next 2 big projects and we'll talk about that.